Okay, so let's continue with the rest of the elementary perceptual tasks. The next task is decoding area. You will probably have seen a lot of graphs that require the user to decode area. But do you know if this is a difficult task or an easy one? Let me ask you to perform a very simple task. If the area of the small circle is 1, then what is the value represented in the bigger circle? Well, let's see the results. Actually, the area of the second circle is 6.25. What value did you guess? Feel free to leave a comment with your previous guess. I bet you probably said something smaller than 6. And that would be normal because actually the difficult part here is because the relationship between the radius and the area is quadratic. That means that for a circle that has a certain radius r, if we draw a circle whose radius is 2.5 times bigger, as this case, the area will not simply be 2.5 times bigger. Actually, in this case, it's 6.25 times bigger. This is what we call a nonlinear relationship. And our brain is super bad at figuring out nonlinear relationships between variables. Actually, even though our brain is so bad at decoding areas, we need to decode areas in a lot of popular charts. For instance, in a pie chart, the values of each variable, here A, B, C, are encoded in the values of the angles. And that effectively means that the area of each one of the slices will be proportional to the values as well. So here we are decoding area as well as angle. In figures like this one, for which I don't know the name, so I just call them human infographics, the values depicted are also proportional to the area. In this case, for example, 75% of the area of the figure is colored red, so here we are decoding areas as well. And also, in a very popular type of plot that we have mentioned before, the bubble plot, also relies on decoding area. In a bubble plot, the area of each one of the bubbles is normally proportional to some variable, and that means that to get the information of that variable, we need to decode area. The next task is decoding curvature, and this is a very particular one. Let me show you with an example. Can you see these three scenarios here, these three sets of curves? Let's say that the green line represents your income, and the red line represents your expenses a long time. Then my question is, can you tell me which is the evolution of your net gain, so your income minus your expenses, in these three scenarios? Actually, I'm going to give you the answer because it's almost impossible to get it right. The actual differences are these ones here. Can you notice that the three scenarios on the left were very similar among them, yet when we calculate the net gain, the difference is huge? Were you able to predict such differences? Actually, if you didn't, don't worry. The problem with curvature is that we tend to calculate differences of curves along the horizontal and vertical axis, as if our eyes wanted these two curves to match, no matter the direction in which the shift needs to be done. Our brain only wants these two curves to coincide. But when calculating differences between such curves, only the vertical differences are of interest. This is what we should be doing to get the values right. So what happens is that we get very surprising results when we observe the actual curve differences. So judging differences between curvature is a very difficult task, and we would be much safer by just plotting the differences instead of leaving this very hard calculation up to the reader. If we look carefully, we will find examples of line plots in which a subtraction of the curves has to be done. Any line plots where the user has to calculate differences are dealing with curvature, even though they are hidden. But also there are some other graphs in which curvature is important even if it's not the primary task. For instance, the chord diagram or the radial bar chart. For instance, take a look at the radial bar chart. In this plot, the outer ring is made of bars which are curved. The primary task here is to judge the length of the bars, so our data is encoded in the length of the bars. We already know that judging length is an easy task, but if we add curvature on top as a secondary task, then it becomes much more difficult. Actually, we will discuss this kind of plot in a later lesson. Okay, so now let's see how good we are in judging volume. Here the task is, if the volume of the small cube is 1, what is the volume of the bigger cube? Well, I wonder what did you say? Actually, the volume of the second cube is 3.375. So in this case, we suffer from the same problem that we had in areas, but even worse. In areas, we said that the relationship between the length of an object and its area is quadratic. Well, when speaking about volumes, the relationship between the side of the left box and its volume is cubic. That means that if the side is x, volume is x to the third power. And as you can imagine, we are very bad at judging cubic relationships, so we are terrible in judging volume. Thankfully, there is no typical plot meant to decode volume directly. That means that we don't have plots where the magnitude is encoded directly in the volume. However, some plots use objects that have volume and trick us into thinking that we would need to decode this volume, like in this bar chart here, where the variable is mapped to the height of the bars, as it is done in any bar chart, but because there's this 3D effect and the bars are cylindric, they have a volume, so we will have a hard time judging these values correctly. Actually, I found this example the best possible way to illustrate how bad we are in judging volumes. This plot is trying to make us aware of how different 5 ounces of wine might look like depending on the glass. So here, all of the glasses of wine have the same amount of wine, but they certainly look very different. The next task is decoding shading. In this case, the task is, can you order these shades of gray from lighter to darker? I'm just kidding, you will have probably noticed that they are all the same shade of gray. But actually, this is not as easy to see because the background of each square is different. The take-home message here is that we are not very good at judging shading because the surrounding colors will affect our visual perception of shading. A type of graph in which we have to decode shading is a choropleth map, for instance. In this type of map, each of the regions is shaded in a light or dark gray, and this encodes the value of our data. As we have seen, this is not the most reliable way to show this information if we want the people to get the values right, because every region might be surrounded by different colors, and this, we have seen, affects our perception. And last but not least, the 10th elementary perceptual task is decoding color saturation. Well, in this case, the authors talk about color saturation, but I believe we could speak about decoding color in general. In this task, can you tell me if these two states that I'm pointing with arrows are the same color or not? Actually, they are not. The one on the left, which is Colorado, is on the range 2050. West Virginia, which is the one on the right, is on the range 5100. Some of you might have got this right and some of you might have not. Actually, it's very difficult to distinguish color saturation. As happened with shading, it is confusing because the perception of the saturation of a color strongly depends on the colors of the surrounding elements. So even though judging color saturation is difficult, we have to do it many times. In choropleth maps like this one, for instance, or if we talk about decoding color in general, we might have to do this anytime that we use colors to differentiate categories, like in this bar plot. In scatter plots, when we want to show a third variable, we might have to decode color as well, and also in bubble plots, as we saw earlier. So actually, these tasks were not that easy to perform, right? Now that we know and understand each one of the 10 elementary perceptual tasks, in the next lesson we will discover which is the ranking from easiest to most difficult.